today's lecture is about linearity. So linearity, once again, how we judge linearity is we apply A x1 plus B x2 and see the output of the system will be same to this. So how we do it? First example is yt equals t times xt. So we once talked that, let's go back to here. So assume that in case of we apply xt, the output of x1t will be y1t. That's a basic assumption, right? And when you apply x2t, the output is y2t. Those two are assumptions, okay? And now we are basing on this assumption. Based on this judgment, we now apply this. Say x3 is given as A times x1t plus B times x2t. This example is given in a book. It's a book, example 1.15. I'm sorry, 17 in the book. So now we try to judge if the system is linear or not. Now we apply it and then put it here. And what will be the output when we apply x3? Okay. So as we apply this, instead of this, so this x will be x3. Okay. So now we have t times A x1 plus B x2, right? So we can find out that it can be A times t x1t plus B t times x2t, right? And now, what is x1t? What is this? In here, right? In here, right. If you apply x1t to here, t times x1t will be y1t, right? So this is y1t. Likewise, when you apply x to t to the system, the output of the system will be y2t, which is t times x2t, right? So t times x2t is y2t, right? So in here, we have A times y1t plus B times y2t. So this is y3, the output of x3t. And output of x3t, which is given like that, will be given as A times y1, which is this, and B times y2, which is, so we can also think them as function of x1, function of x2, which is exactly the same to here. We apply, I use A, B instead of alpha, beta. We apply this the whole of them is x3, and then the output is A times fx1, B times fx2. So this superposition is hold, so we can consider this system as is linear. let's have another example. Now, our second example, is it clear, Christian? Our second example is x1t. I'm sorry, x squared t. Of course, it looks nonlinear, so we know that it's nonlinear. But let's apply superposition to see it. So until here, so let's separate them. Until here, the process was the same. We have assumed that x1t, output of x1t is y1t. Output of x2t is y2t. We'll assume that, this assumption. And we define x3 is given as a times x1 plus b times x2 is the same. And then we apply x3 to the system. And then assume that output of x3 is y3. And now we apply that to the system, so it will be square of this, right? So we once remember to judge the linearity, we check superposition is hold or not. To check the superposition, we follow this process. We have a process that x1 and x2 arbitrary x1 and x2. And assume that the output is y1 and y2. And then we define a new variable x3, which is the constant times of x1 and x2 and plus them. Apply this one to the system, whatever system you have, and then derive. Now what you have, a square, x1 square, b square, x2 square, 2ab, x1, x2. And now, this is the output. And what do we need to hold the superposition? What do we expect to hold the superposition? So let's go back to here. Superposition is like this, right? So ideally what we want here is a times function of x1 plus b times function of x2. This is what? A times function of x1 is what? x1 square. Right? B times function of x2 is what? B times x2 square. So to satisfy the superposition, this y square should same to this. But as you can see, they are not. This is not true, this is not true, this is not true. So they are not the same. So this one does not hold superposition, it's not hold here. So this is not linear, non-linear. So once again, this one looks non-linear for sure. However, to judge the nonlinearity, you have to follow the superposition process, define x1, x2, x3, and then put x3 to the system and find the value that you want to make the superposition and check if they are the same or not. That's how we judge the superposition. Okay? Right? So now we have to introduce some energy and power of the system. Is it clear? Okay. Now we have instantaneous power of energy. This is defined. This is definition. So power and energy is given as the voltage times current. This is for sure. This is for sure. What if if you have a total power, something called, this is the signal that when you have a time domain, the voltage can be like this, and current can be like that. This is the point. This one shows the point at arbitrary t. Right? This one shows the power at certain point, say time of t, they have a power at this line, and another t, they check the power at this line. So this one calls instantaneous power. In case of total power, means that how much power is attenuated or used between two time intervals. How much is the total power between this time? They are defined as integration of time 2. We just add them all together. What if you want to have average one? Average is what? Average is adding everything divided by the time. So average will be over this total power. Right? So those three definitions on the screen is shown in here. Shown in here. So we have instantaneous power at certain point. This one defines the power at certain point t. When t defines 0 second, 1 second, 2 second, they give a value at the point. This total power add the power from certain point, say 0 second to 1 second, or 1 second to 10 seconds. This is total power, and this average power is total power divided by the time to get the average. So one step by step. What about this? So in case of continuous time and discrete time, they define a little bit differently. Sometimes we have this power, however, we sometimes have to get the absolute value, because in case of the average value, we add plus and minus. We think about polarity. So even though we consider that, okay, there is a, let's have two examples. Say this is one signal, and this is second signal. Assume that this yellow and white looks very differently, but the average will be the same, right? Plus and minus, so it will be 0. So average is a very good indicator to define how the signal looks like. However, they does not show you everything. So that we sometimes introduce another value, something called root mean square. Like we square the signal, average them, and root to find their actual amplitude. Or we sometimes introduce something called average of absolute value. Because if you do that, then this yellow and white will be quite different, because this absolute value or square, they will make this plus and this minus will be same amplitude, and make this yellow small and this white large. So we can define another one like that. So the one in the screen, they show another value like that. We have the same thing. Same thing to here. We have T1 to T2, but we have introduced absolute value. now square. If you don't have it, then they correspond to this. So in this line, they consider plus and minus. In this line, we don't consider plus and minus. We just care about the amplitude. So we have another value like that. In case of discrete time, it's quite similar, but sometimes quite different. Only difference here is in discrete time, I explained that integration becomes summation, and there can be xn. N is a discrete time, and there can be absolute value starting from n to n. Let's say n to n. K equals minus n to n. And this value, typically there can be 2n, but actually it's not. 2n plus 1. Why? Because from minus n to minus 1 is n. From 1 to n is n. We have 0. So I'll add one more point. So the count from minus n to n is actually 2n plus 1 points because of the 0. So that's the reason we add 1 in here. Right? There's a definition to get the absolute square 1 in discrete time. So this is a definition, so you have to worry about that. The thing shown in this slide is we mainly talk about continuous time by far, and discrete time has a lot of similarity, a little bit different, but they have a lot of similarity, almost the same, except we use integration versus summation, and we use differentiation versus subtraction. So only notation was quite different. They have similarly looking things, but there are several properties that discrete time and continuous time may be different. One of the things like that, we just simply subtract them. In here, we have to add 1 point because of the 0. It doesn't happen here. Another interesting point is exponential. Let's introduce exponential in continuous time, which we have very familiar with. They have e j omega 0 t. Let's have it. And let's have e j n over 2 pi n, like this. What will be similar or larger? What will be similar or different? One of the trick is I always write down in my slide. So let's see them in this way. In here, this is periodic signal, right? Periodic signal. So we usually increase the time, right? So we increase the time at a certain time and find the periodic signal. The periodic signal is given as how much? So if t, and this omega has a relationship, right? If t hits certain point, like 2 pi divided by omega, there will be repeat. So we usually consider the time in this case. What if we change omega? What if we change omega? For example, if we increase omega to 2 omega 0, if we increase omega to 5 omega 0, what happens? If you change the omega, then the frequency keep on increase. So say that they initially looks like this, then they will be looks like that, they will look like this, that looks like this, and they become faster oscillation. So basically we change their frequency. in continuous time. In discrete time, how about that? Let's rewrite them. In n, if you change n, they're pretty similar. Same to this. If you add a certain number of n, then if n hit certain point of omega, then they will repeat. So in time domain, n over t, they were pretty similar. In case of frequency, let's consider j omega 0 plus 2 pi. In here, we say if you change the frequency, either increase or decrease their frequency change, right? In here, we are increase the frequency, right? We have a frequency plus certain value to increase the frequency. What happens? In here, E j omega 0 n times E j 2 pi n. Right? And what is this? 2 pi n is 2 pi, 3, 4 pi, 6 pi. So cosine 2 pi is what? 1. Sine 2 pi is what? 0. So this one equals 1. Right? So means that this one and E j omega 0 n is the same. So remember, at this point, we does not change time domain. In time domain wise, when do you increase time domain, the value of time, then of course they are repeating. This one, we change the frequency, right? When you change the frequency of continuous time, their frequency keep on increase or decrease depending on the value you apply. They keep on change. In case of discrete time, they are not. What they says now here is, even though we increase the frequency, they will be the same with the lower frequency value. This one and this one are different frequency, right? Omega 0 plus 2 pi versus 2 pi. I'm sorry. Omega 0 plus 2 pi versus omega 0. They are different frequency. This is a higher frequency. However, the actual signal will be the same, meaning that in case of discrete time, different from continuous time, they have repeating frequency. What it says here is the frequency itself, even though you keep on increase the frequency if you increase the frequency in discrete time exponential signal, their frequency sometimes increase and then they decrease, having some period. That's one of the difference. So let's see it. So this is a signal showing that discrete time signals. So remember that only difference here is they increase the frequency. Remember, they have frequency of 0, frequency of pi divided by 8, 4 pi divided by 4, 2, so meaning that this one, like this, they starting the frequency 0, pi over divided by 8, pi divided by 8 times 2, pi divided by pi times 3, pi divided by times 4. So pi divided by 8 is the b over there. Pi divided by 8 times 2 is what? 4, right? So it's here. And then that is we keep on increase this to increase the frequency. So when you see here is, this is the initial condition and this is after they have some increase. Same, right? Repeating. So if you increase the frequency, they change. Actually, they are become faster, right? So this one is the DC. Now they are like a sine wave like this. Now they are faster sine wave, right? Faster sine wave. If you keep on increase, they become even faster. And then suddenly and then we can slow down, even slow down, which is the same to there, and even slow down, same to here, and go back to original condition. So showing that is keep on repeating in one cycle. So what this one shows here is the second point in here. In case of discrete time exponential signal, they are repeating not only the time domain, but also in frequency. If you increase the frequency, I'm not saying that they does not increase. When you increase the frequency, they actually become faster and faster, which is increase the frequency. But they have a period. They go back to their original condition, slowing down. So keep on increase the frequency in discrete exponential signal does not guarantee that you keep on have a higher frequency. So that's one of the major difference in discrete time and continuous time. Okay? Questions? Oh. Okay. So in here, we already know that, but let's rephrase it. So to this, let's go to time domain. We increase the time domain signal to find the period. The page is page 34. E, J, omega 0, and to make them same, what do we need? This one is actually given as J omega 0 n, right? So to find the period, we have to make this one same to this, meaning that this one should be 1. This one should be 1 when this one n times omega 0 becomes 2 pi, a constant times 2 pi. When this one becomes constant time 2 pi, 2 pi, 4 pi, 6 pi, then this one becomes 1. Likewise, what we see in here. Of course, we are talking about time domain now, not talking about frequency, right? So this is now we are in a period. So this n is what? N is when you add in time domain, this n is the time that this signal can be repeated, meaning that this can be a period. To get a period, it can be 2 pi omega 0 times k. They were given as m in here. So let's have m. And the period will be smallest number of n should be 2 pi over omega 0. So this is same to continuous time, right? In continuous time, our period pi divided by omega 0. So it's the same, even though discrete time, the value itself is same to continuous time. The difference here is, in case of if you increase the frequency, exponential in discrete time, they become periodic even in a frequency-wise. Okay, that's it for chapter 1. Any questions? Right. Let's have chapter 2. So let me rephrase the chapter 1 more time. In chapter 1, we introduced several system properties. We now select 2 properties. Time invariant. Time invariant meaning that the input and output relationship does not change by time. They maintain by time. Linearity. Second one is linearity. Linearity means when the superposition holds. Superposition means when there's A x1, B x2 inside when given as an input, output will be additively and homogeneously given. We now introduce a system called linear plus time invariant. So this system, the discussion we have in this chapter and probably afterward, we already assume that this system is linear and time invariant. So we open the second chapter, linear time invariant systems, in short called LTI system. So before we move on, we introduce impulse output. So we once talked about that. Let's have an example right here. So let's have some discrete time signal. Let's have some discrete time signal acts like this. Looks very arbitrary, very unpredictable. -4 going down, -3 goes up, +2, -2 goes up, goes down, blah, 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 going on like this. We can consider this system as a segmentized system, meaning that this xn can be a summation of multiple x systems. Say one signal has only signal like this. Second system like this, like this, like this, like this. And we can consider this x1 as adding everything together. So let's forget about this equation right now and consider only the signals. This x2, this is the signal that has a point x2, when -2 only. This is the case that we have only 0. This is the case that we have only -1. This is the case that we have only 1. If we add these four signals together, then this one is same to here. This one, -1, will be same to here. This 0 will be same to here. This 1 is same to here. So if you add these four together, that means it's same to these four, right? You have more signals like -3, -4, 2, 3, 4. If you have more signals like this, if you add them everything together, you can this original signal. So what this one says now is, one of the point of view here is we can pick each point and divide into each signal having only one point, and consider this original signal is summation, sum of all those separated signals. We can consider them like that. How do we find out the individual signal? How do we find out each signal from his point? We are introducing data function. We have a data function before, right? So let's have an example. Let's open this. I try to redraw it. 0, 1, 2, -1, 2, -2. Okay, let's have only I try to redraw it as close as possible in my point of view, and this time. How we pick up each point? How do we pick up each point? one way you can do here is, let's rephrase this n as k. N is integer, k is integer, so it doesn't matter, we just change the value. And let's introduce delta function. Delta function is what in discrete time? Delta function is what? They are 1 only at 0. That's delta function, right? That's delta n. Let's find out. Using this delta function. Let's find out what is delta n minus k. Assume this is k. So hard to think initially, but let's think about one by one. Let's say we have n equals 1. Let's say we have n equals 1. That means our current n is a time domain, this time domain value corresponding to t in continuous time, right? So assume that we have a time at 1. And delta n minus k will be 1 minus k, right? In here, what is it? Delta, remember, delta is 1 when the value inside here is 0. So what is k making this 1 minus k 0? 1, right? So meaning that this one is 1 at k equals 1. Okay? So remember, these two are same scale in k. If you multiply them, so this is a function xn initially, but we are using k now, so can be called as xk. And now we introducing delta n minus k, arbitrary number of n. Assume current value of n is 1, now is delta 1 minus k, which is like this. If we multiply them together right now, xk times delta n minus k, currently n is 1, what happens? If you multiply them together, what happens? This one times 1, right? Other thing is 0. So we will have same amplitude of xk when k is 1. So now we are picking up this point. Other than that is 0. One more time. When n equals 2, delta function will be 2 minus k, right? In this one, when k is 2, delta function is the value to the delta function is 0. So delta function will be 1 when k equals 2. So this is 0. Everything is 0 except a point of 2. If you multiply them together, the output will be, sorry, too short, but this value will be same to this value in here. Other than that, it's 0. So what you can see now here is, so we can keep on changing this n. To find the right value. So what you can find here is, if you have multiplication of arbitrary signal, any signal, multiplied by n minus k, we pick up at point of x, and what we learned in the last page, if we add them together, from minus infinity to infinity, this multiplication is what? We pick up point of each point in the signal. If we add them together, they can be our original signal. All right? So that's how this equation comes in. So those equations on the screen, the x point, the signal x, can be also viewed as multiplication of this signal times n minus k. This delta function gives you a function that we can pick up a point from original signal, which is a very straightforward concept, right? But this one will repeat when you drive Fourier series and other functions. So this derivation is, I think, is quite straightforward, but give you one idea that how the system functions. So I think you may hear already about H function. We already talked about that H response, H1 as something called like the transfer function, things like that in previous chapter. When you talk about the boxes for cascade and parallel, we say H1, H2, multiply, adding together. We already know that our box can be represented as H. Why? Why we consider H? Why we model those system as H? Why we call them as impulse response? Impulse response sounds familiar, right? Impulse response. Why we have those names? There's a reason. Let's go back to box. And this is our input, and this is our output, which is shown here. Assumption is this is a linear time invariant system. We does not apply this one to nonlinear system right now. So say that this is xn or x. Okay, this is yn. How to model this? How to model this? Before we start, the transfer function is given as when you apply the delta function as an input. Output of the system is given as h. Well, we'll see it. So this h means when input is delta function, output is h. And this output h, when you do the frequency domain, they can be h, the same one. So this impulse response, the name is given because our input is impulse, sequence of delta function. Because it's impulse, right? We give an impulse. And response from those impulse, output of those impulse is h. That's the reason this one's called impulse response. And why? Let's have some derivation. Assume that this output y is given as some transfer function inside, some function of xn. Assume that they're given like this. Okay, this one. And remember, this can be modeled like this. Okay? So we can have sigma x k times delta n minus k. We can do that. And this is linear time invariant system. What is one of the property of linear system? Superposition, right? So we can see them as this many of these are added inside it. One, something plus, something plus, something plus, something plus. So we can, this is a linear system, we can take this out. So I'm following this. So as this is a linear system, we can take this out, right? So we are taking this out from the system. Like this, okay, because it's linear. And then what? Like this. Here is the function of k. This one don't have any relation with k. So we can take this one out. Because it's a linear system. Think about superposition. Superposition is what? There's addition. We can separate by addition. When there is constant times function, we can take the constant out. So we can take this out. So it's k x times transfer function delta m minus k. We cannot take this one outside because there is a k is restricted here. So we can rephrase that as, what is this? We have t is what? T means function that this black box works. We have input of delta m minus k, which is delta. Inside there is inside it's a delta is an integer number, right? We can consider them. The input to the system is delta. Output of system is h. So output of this will be the output of the system when input is delta m minus k. So this will be h m minus k, right? Because if you have delta as an input, the output will be of the system will be hn, based on this definition. This is the definition of impulse response, right? So because we have m minus k here, we have m minus k here right now. So that will look like that. So finally, we have final value, say that x k times h n minus k. So that's it for now. So hkn means n minus k here. So what is the meaning of it? What is the meaning of it? This one gives you an idea that how to bridge two systems or how to find the output of the system. First, let's go back to why we care about impulse response and why we think impulse response can represent the system. Let's go back to here. In here, we once say that if you multiply n, the signal by n minus k, this is n minus k, right? xk, k equals minus 2, n minus k, n plus 2. Likewise, k equals 0, n minus k is n, just n, like that. K equals 1, n minus k is n minus 1. So this one shows xk times delta n minus k. What this one shows here is, if you multiply the original signal with a delta function, then we can have a function at each point. We have value at each point. So if you pass that input to the system, we can value of the system. Once again, assume that this is your system. This is your system. By applying the delta function as an input, we can pick up the value at each point of the system. So by applying the delta function, the output will be same to the system, right? That's the reason we consider impulse response and think impulse response is a representative of the system. Because when you apply delta function, output will be same to the system, right? That's the one reason. That's the reason we keep on using H as a transfer function. Because transfer function is the output of the system actually, but output of the system will be the same to the system. That's the reason. Second, if you have, now we are not applying impulse as an input. We apply arbitrary x as an input. If you apply arbitrary x, and if you know the impulse response, by multiplying them together and summing from minus infinity to infinite, we know the output of the system. So if you know the impulse response, which is representative of the system, if you know what is H, then any arbitrary input, you can find what's the output of the system. That's the reason we keep on saying H is important, how to drive H function is given like that, what's the value, blah, 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 all of things comes in like that. Because H is representing the system, and if you know does H, any input is applied, you can find the output if this equation holds. Assumption, this is linear time invariant system. If it's not linear time invariant system, this one does not hold. It's only valid for linear time invariant system. Okay? So let's have an example. Assume that can you see it? Can you see it? Okay. This is our X, our input. This is our impulse response, which is symbol of the system. What is the output? So once I mentioned that, if you know the impulse response, which we already know it, you should know the input, right? And you try to estimate what's the output. To do it, you just multiply them together. But we cannot multiply one by one because, remember, this is similar to the moving average. Depending on the k value, this value and this value will be different, right? So we have to shift. This one is fixed, remember? Now let's go back to here. Let's go back to this one. This one, let's go back to this. Remember, we have x, and we have delta. When k equals 1, this one only picks up here. When k equals 2, this one only picks up here. So in here, x does not move, x just stays. But delta function, which is delta function right here, they shift depending on n. When n equals, n equals 1, n equals 2. When n equals 1, they will look like this. When n equals 2, they will look like this. So this one, they shift in time depending on the value of n. Similar to here. It looks almost the same, right? Y is correspond to xn, right? And here is xk, and h is corresponding to delta. So now what you can see now here is, okay, x will be the same. X will not change by k or n. They change by k, but they does not change by n. But h will shift by value of n. So the logic goes like this. So let's find out when n equals 1. Let's find the value of y when n equals 1. y is the value. To find this value, we have to check xk, which does not change by n, and adjust shift h when n equals 1, shift h to the position that n equals 1 and multiply them together. When to find n equals 2, y2, when there is n equals 2, what is this value? Even though n changes, x doesn't change, but h should shift because this n should be 2 instead of 1. So they shift and multiply them together and add them together. So let's have how it looks like. So this is n. Also this is k, doesn't change. And this is h. But depending on the value, they should shift. So they shift by -1. You can see that this one shift. This one goes to here, this one goes to here, this one goes to here. So depending on the k, this one should change. However, let's see how they functions. Let's go back to here. In here, once again, when you talk about this, to get x point, assume this is x, -1 goes down, 0 goes up, 1 goes up. We pick up -1 goes down by having x -1, delta, and -1, and +1, like the one at the right side over there, corresponding to this, which is corresponding to this. And in case of this, we pick up this value, is corresponding to this. This one, we pick up this value, which is corresponding to this. We apply this to the system. When you apply to the system, this one will change to h. Let's think about the difference. This one is representing the x, and this one, when this one changes to h, then the output will be the n. To get n, we apply this to the system when they change to h, and see how they changes. So they will be multiplied by this, and this one they will multiply by this. This one they multiply by this by shifting in time domain. After they finishing them, we add everything together to get this. So this one is what? This one is value that when k equals -1. The second one is the value that when k equals 0. This is a value that when k equals 1. So when you add them together, this is really long. Say that in -1 point. This is really long in minus. This is a little bit in minus. This is not so. It's pretty long in plus, but not so long like this. So adding this, we expect we have some minus in here, so which you can see in here. In this point, 0, this minus and this plus is almost same amplitude, and this is 0. So if you add this 0 will be cancelled out, and this is 0, so we expect 0. So this is what you can see here. Likewise, in here there is a small plus, big minus. So if you add them together, we expect a big minus. So this is what you can see here. So what this one shows here is this left side is representing the x, which is this. X can be segmentized. They can be separated into each point. Multiplication will be each point at n equals 1, n equals 2, n equals 3, and this side is delta. So this right side in this slide is showing each component of x. when this one is x is given as an input, passing through the system comes as an output. Output will be given as x times h, which is shown at the left side of the slide. So when the right side is given as input, what is corresponding output? So they match one by one. When this one is input, this is output. When this is input, this is output. When this one is input, this is output. Because this is a linear system. If it's not linear system, we can do it. And then, so we are finding y by each component of this. And then we add them together to find y, which is given as we add this together to find this by superposition. That's how this function goes. Questions? So the concept here is basically we divide one signal to multiple signal, passing each signal individually to the system, find the output individually, and add them together to find the final y. That's how the system goes. Also, our second assumption, I keep on emphasizing that this is linear time invariant system and time invariant system. We used linear function, linear property, because to maintain this claim, this one should be linear. Now we are utilizing time invariant property. As this one is time invariant, this one does not change by time. Of course, that's not meaning that they are stable, that's not meaning that. They are changed by time, but even though you shift by time, their function does not change. There's a claim here. So, what this one says here is, because of this, in here, this is different from Hn. This is time-shifted version of Hn or Hk, right? There are Hn minus 1, n minus k, and Hk, they are time shifting and reversal, right? Even though they do that, this one should not change. Even though they shift by time, if they shift by time and they change by shifting the time, which is not time invariant, then we cannot use this claim because this Hn minus k will different from Hk. So to utilize this claim, we need assumption that this system should be time invariant. Okay? So, once again, this is possible because this system is assumed to be a linear time invariant system. Each Hn, which is shown in here, is often called impulse response, or the full name is unit impulse response, because impulse is delta function, which is actually value of 1, so it's called a unit. So full name is unit impulse response, but often we short the vocabulary to be just the impulse response, which is representing the system when the input is delta, the output is Hn, the Hn is same to the system itself because the delta is picking up a value at each point. Yes?
네.
모양이
네, 맞아요.
이렇게 막 똑같아야 될 것 같은데
네, 뒤집혀서 그래요. 이게 그죠. 한다고 설명해 줄게요. 네.
So, the question was why this one looks a bit different, right? So I will talk about that because we only have 5 minutes. So we'll finish the lecture and talk about that later. Now we have this property, and using this, we introduce one important concept called convolution. So often called convolution sum, but in short we call as convolution. Convolution is So we keep on have repeating form. We keep on have repeating form. Say sigma from minus infinity to infinite, xk, and h n minus k. So we can have same to here. If summation from minus infinity to infinite, xk and n minus k. So assume that we have a function y, let's have a y x1. And function, we have two functions. Convolution is like addition, subtraction, multiplication, those functions. If you put this star mark, that's meaning the convolution. Convolution is what? Select one of them. We first add summation from minus infinity to infinite and another k, usually use the k, and select one of them, and second one is given as n minus k. So two steps. First, three steps. We put summation of k from minus infinity to infinite. So this is definition of convolution. We pick one of them, put k, pick the second one, put n minus k. Likewise, if you happen to put the second one, does not matter. You just put them same way from minus infinity to infinite, x2, k, and pick the first one which is left over as n minus k. So this is definition of convolution. And here is what? And here we can rephrase them as xn equals x n convolution of delta n, right? In here, we can rephrase them as yn equals x n convolution of h n. So that's the simpler way we can define convolution. And of course, as I said here, as this is convolution, this is exactly the same to the case that when we pick h, when you pick the h, there can be x minus k. They can do the same meaning. So one of the tricks you can do here is select something. If you see those two signals, select something looks simpler at this side. Because this one does not change. When you do the convolution, you have to draw some picture and keep on shift to find the values. This one does not change, does not shift. This one we have to shift. So picking up signal looks simpler, that is moving, is make your calculation simpler. So that's a trick. Pick something looks simpler to this point. In here, this one is much simpler than this. So this one is picking this way. Okay? So this is definition of convolution. In case of, this is for the discrete time. This is for discrete time. In case of continuous time, this one is called convolution integral. Convolution integral is what? There will be discrete time summation, there will be some integration of certain values. They will be the same. How we do it? If you try to find, so I will cover this one later on Thursday. But what you do here is, if you try to find the convolution of these two, this one and this one, which looks simpler, this one looks simpler, right? The bottom one looks simpler. So let's pick up this one to n minus k. And first one, the upper one, as x. So keep this one as x. So you keep it as x. Change this one to k. And this one should be n minus k. So the x's will change to k. So what happens now is they shift, they reversed. Because it will be change from n to minus n, right? And then depending on n, we shift this one. This one is when n is 0. This is case that n is minus 1, n is 1. So we keep on moving that depending on n. And we multiply this by this to find the value of n equals 0. Multiply this by this to find the value of n equals minus 1. Multiply this and add them together to find the value of n equals 1. And that's the final value.